Welcome to this video. In this video, we're going to attempt to write a compressor in one take. What we have here is actually the first episode of Silicon Valley as a text file, and the goal is to compress this and make it smaller. So let's take a look at this file. We got 11 kilobytes. So our goal is to try to make this file smaller. And hopefully we can achieve this. So let's begin. F equals open pilot txt read binary. Okay. We're just gonna dump it into memory. Let's just see if we loaded the file. Let's open up a terminal. Let's add the shebang, user, bin, user, and is it? Actually, I think it's this. Tiny. All right, cool. So we got the bytes. All right, so next up is count the frequencies of letters. Which is just counter memory. All right, so these are all the ASCII characters. All right, next up. Let's get a priority queue going. For letter and frequency. Right, I'll call it heap. For letter and frequency, we are going to push. We're going to go heap push. Into heap, we are going to push the frequency, and then we're going to push the letter. $38 is like end of line byte, I think. 42. Or rather, star. So there should be 1 star. Just to double check. Yep, there's just 1 star. Cool. All right, so next up is we gotta push stuff. Into the tree. First, I guess we got frequency 1, and then we got letter 1, which is just heap pop from heap. Frequency 2, letter 2, heap pop from heap. By the way, we're doing Huffman encoding, so make sure you guys know what Huffman encoding is. All right, so we popped the 2 things off. Next up is we got to get their sum. Frequency sum is this. We got to create something called a node. So let's create a node. Class node. Def init. What does a node have? A node has a left child. Actually, we're just going to do it here. Node has a left child, right child. It's got a frequency. It's got a value. It's got a code. It's going to have a left, which is just nothing. Right, which is also nothing. Code is also code is just an empty string. This should be good. This is going to be just left. This is going to be right. Self.frequency equals frequency. Self.value equals value. Self.code equals code. Def less than. Do we need this? Yeah, I think we need this. Not sure what this returns. I think here we actually gotta push a node. Letter. Oh, I guess I should have deleted that. Yeah, let's print here heap 0 value, or v. Oops. Heap 0 1 52. That looks about right. That looks about right. Okay, cool. So we're pushing these guys. Cool. All right, next up is we gotta get, gotta create a new node with just these guys. We are going to push -1 for the value. No code. We're gonna have left and right. So here, and we also got to push it also. Heap push. Heap node. Here we should have just one. Tuple. Oh, yeah. I guess we gotta go node.f. Print heap 1. Oh, 1. All right. So it looks like it works. All right, so now what do we got to do? Now we got to build codes. Let's go build or gen codes. So basically the things that are at the bottom of the tree are things that appeared the least amount of times. And those things are going to have the longest codes. So generate code, we need a root node. We need a running, and we need a code. And the way this is going to work is basically if not root left and not root right. So if it's a leaf node, we're going to say root.code equals code. Otherwise, we're just going to gen codes on left with code in 0, and then root.right code. I'll give it a 1. And root is going to be whatever is left over in the heap. Nice, so we got the codes. Let's also create a like a map, code map. And what's going to happen is we're going to say code map at root.value is going to be code. Let's see if we can print code map. Of course, after we generate the codes. All right, cool. So 32, I think that's a space. Yeah, 32 is a space. What's 110? N. N appears a lot. 112. P. Oh, interesting. You'd think like the letter A would appear a lot. I think that's like 97 or something like that. $76. All right, well, that looks legit. Looked kind of small, but whatever. Okay, cool. So we got the map now. So I actually got to encode this stuff. So, byte in memory. So there's kind of two ways to do this. There's like a goofy way, and there's like a proper way. We're gonna try to do this the proper way right off the bat. Or maybe we can do it the goofy way first, and then yeah, there's actually another piece we gotta do. We gotta generate the tree. Yeah, generating a tree is kind of fun. Let's go def gen tree root if not root left and not root right. You can actually probably save time by just saying this thing here, or I guess leaf can just be this, and leaf that is leaf equals true. And just basically saying root is leaf. Cool. So if root is leaf, what are we going to do? What are we going to do? We're going to output 0 followed by root dot value. Else we're going to return, we're going to do a post order. So post order means gen tree left a 1 to indicate that it's a parent. So you're also going to generate the tree. See what this tree looks like. You guys think it's going to be a good tree? I think it's going to be a good tree. Whoa. No. Yeah, that kind of looks like a fun tree. The only problem with this tree is that it can't be strings. It's gotta be bytes. Yeah, it's gotta be bytes. Ah, no. See, the problem with this is this creates the thing. So you gotta do root v 2 bytes 1. Byte order. Ah, we got byte order. I'll just do a little. Little bytes are good bytes. Yeah, see, there you go. That's a way better tree. Alright, so start getting the output file actually ready. Just gonna open up output dot Boris, that's my name. Write binary. We're gonna say what we're gonna do is we're gonna write the tree length. Out write, and we're gonna write yeah, we're gonna write the length of this tree. Well, it's an integer. So we're gonna write length of Huffman tree. We gotta actually write the tree. So we got the length of the tree, we got the tree. And now we can start encoding. For byte in, what do we call our input? So this space looks ugly. We called it memory, I think, or something like that. Memory, yeah. For byte in memory, code equals m code map at byte. So now we gotta write the actual bytes. So we gotta have like a byte. That's a 0. What we're gonna do is packed equals 0. So for bit encode, so basically we have 8 bits in a byte. like this. We're gonna start packing them from, I guess, right to left. Let's go. So a bit code. How do I get the codes? Our codes are just strings, right? Yeah. Yeah. So if bit is 1, bit is 1, we're gonna say byte or equals byte or equals 1. So we're gonna set this thing to 1, and then we're gonna say byte shift left 1. And we're also gonna say packed plus equals 1. And basically, we're going to say here if packed is equal to 8, you're going to go out.write, and we're going to write, we're just going to write the byte, to be honest. Yeah, we're going to write the byte. And we're going to say byte equals 0, packed equals 0. Bit equals 0. We just shift left. And if packed is less than 8 here, I don't know what else we gotta. I think this is the case actually for both of them. Yeah, so if packed is less than or equal to 8, I'm just gonna write the last byte. I want to actually small txt hello world, this is a test, and then we're going to test it on something small first. Bytes like object. Oh, well, I guess since we're only packing a byte here, we're only going to write a byte. So we're only going to write a byte. This might get a little. C and C++ this would have worked, but now I gotta do this thing. Int too big to convert. What kind of black magic do I have to do here? Oh, there you go. How does that look? Let's see. That looks okay, I guess. So our goal, I guess, is to try to now read this thing and parse it back. Yeah, it'll open and it'll close. And I guess it closes by itself. Yeah, so our goal is try to read this back and rebuild the tree and parse this thing. So okay, so let's try to be smart about this. I don't want to rely on any of the stuff I did here, like the code map and stuff. I'm only going to try to rely on these functions and the node definition. So first we got to read the length of the tree. So let's go encoded, open, let's get my output, read binary, and I'm going to try to read an int. Data equals encoded.read. So it should be bytes, I think. So I believe we got like tree size is just we do this. Does this kind of stuff work? Unsupported operation read. Well, I can't do this. Why not? Open. Read. Oh, oops. And from bytes. Well, yeah, I don't think that worked. Oh. Should we try to like tiny unzip? Put the thing here. Alright, so we got 35 bytes as the tree size. Let's make sure we're reading the thing correctly. What is the tree size here? What does that look like? Oops. 35. Alright, good. So we got length of the tree, I equals 4. And equals 4 plus tree size, while I is less than and. So here we need a stack. Now we're basically reading the post order thing. And the idea here is that if we encounter 0, which the byte should just be 0. So if yeah, basically data at I is just straight up 0. We want to push. I just want to create a node. Yeah, we want to create a node. Node frequency doesn't matter. Value doesn't. No, value does matter. It's data I plus 1. Someone's calling me, but I'll answer it in a bit. Yeah, did we print the 0 first? Yeah, we did. We got the 0 first. Is byte 0 equal to 0? No, it's not. I guess we got to do this then. What was I doing? I was checking if we did the 0. Yeah, okay, so we did the 0 first. So we got this thing, node, no code, nothing, nothing. We could say that n is leaf is true. And we just do stack dot append n, and we go I plus equals 2. Else, we got right child, which is just stack.pop. We got left child, which is stack.pop also. We gotta construct another node. And this node, we got left and right. And here, we're gonna push that back onto the stack. And then we're just gonna increment I by 1. And then here we should have the length of stack here should just be 0, I think. Or 1. Yeah, it should be 1. Where's tiny unzip? Yeah, index out of range. Yeah, it's our tree. And there's a bunch of ones. Yeah, this is our encoded data. I mean, ideally we should have ideally we should have some stuff. This is a byte. I got 2 bytes. And was it just empty? No, it's empty. Are we writing the tree correctly? Oh. It's not a... While I is less than and. What's tree size? Oh. Data. Tree size is 0. We can do this the bit shift way. Should we do this the bit shift way? Yeah, I guess we can do this the bit shift way. The bit shift way is basically, I'll leave that in there. It's like data at 0, data 1, data 2, data 3, too lazy to do math, what? Index out of range. It's 24, by the way. Maybe the index is out of range. What? This makes no sense. Why is it even printing this? Guys, am I tripping balls? Oh, I guess it's because it's calling. Is it because it's calling this or something? Oh. Well, there you go. So I guess just for whatever reason, when we were importing the node. Oh wow, that's... Do this. This feels like we're just doing too much work for something so trivial. There's like order of operations. $35. All right, well, we got that. Tree size, print I and 439. Print data at I. It's 48, so it's not in this, it's in this. Oh, is it this? Okay, so this thing is just wants to be really annoying. I literally compared to 48. Oh, there we go. All right, well, that was really annoying. Let's go root, stack that pop. Just because I don't want that weird issue to happen, we're gonna import this function here, gen codes. Code map is not defined. Well, yeah, I guess we need a code map, I suppose. Nice. Let's get rid of the debugs. All right. Cool. So next is we actually have to read the inputs. So while I is less than the length of data, now we're reading bytes. Bytes. Yeah, reading bytes. So we got byte equal to data I. Then we get code. And what we're going to do is we're going to say for I in range 8. Or no, for J in range 8. So again, we got the byte with 8 bits that are distributed something like this, where this was the first byte we wrote. So here, guys, we're going to say pointer equals root. We're going to basically say something along the lines of if J and 1, we're going to say pointer equals pointer.right, else pointer equals pointer.left. But if we somehow encounter if pointer is leaf, that's right, if pointer is leaf, we are going to print char of pointer.v. Oh, Yeah, this is very wrong. Byte. Yeah, so we do byte, and then we just byte. Yeah, well, this is where it gets fun. Don't need this. Print B. No. Let's see what we're dealing with here. So we get a byte. There are 2 bytes. Byte order. Little. Byte equals this. 2 bytes. Order little. Yeah, that's where it gets a little interesting. Two bytes, one little bxd4. Yeah, so I mean the goal here is to basically parse this thing. Pointer. Cool. I plus equals 1. Um, seven minus j. If byte pointer equals pointer dot right, pointer equals root, pointer dot v, reset the root. So I got the first letter correct. I wonder if we're writing these correctly. I think it is writing them correctly. Pointer is leaf. Print pointer. Might not need to do this. Oops. Oh. I mean, it kind of works. This was kind of a cool idea. Maybe I'm just not writing them correctly. That's like the only thing that I have. Packed goes up. Packed equals 0. Yeah, I mean, if we pack the byte, we don't necessarily want to. Yeah, maybe I encoded them wrong. Byte or equals 1. Yeah, this feels like this feels kind of wrong. If you get a 1, you want to pack. Yeah, so if it's we get a 1. We'll get it. Just a bunch of eyes. It's just a bunch of eyes. That's hilarious. Byte packed. One shift by packed. Yeah, I don't see anything super wrong with this. Let's see here. I'll convert int object to bytes. Why not? These should at least be like different. They're not different. Thing in memory for bit encode. I think I'm just not doing this correctly. Or am I doing this correctly? Bit equals 1. Yeah, so if bit's 1, am I being a noob? Oh, would you look at that? I was being a noob. So we got hello world. This is a test after a debatable amount of confusion. Now we want to actually output that to a file. I'll just call it. We'll call it out. So open output txt. We're not writing binary anymore. We're just gonna do out write, and we're gonna write char pointer v. We got output. We're gonna just do diff input, or I guess small, and output. No new line at the end of the file. I guess the only difference here, which I suppose we're missing, we're missing some little piece here. We're missing the last character. I guess it's not packing enough bytes. But we'll just ignore it for now. We can always fix this later. I want to try to see if we can zip Silicon Valley. So that would be pilot. So tiny zip. That was pretty quick. Tiny unzip. Let's look at the output. Look at that. That's pretty good. And I guess the diff is hopefully we're just missing one line. The new line at the end. Yeah, no new line at the end of the file. Everything else looks okay. Like this looks. And now the moment of truth. How much did we compress the file? Let's go look at View and Finder. We're going to look at this intermediary output file. Got 7 kilobytes and 11 kilobytes. So we compressed it by about 4 kilobytes. We can probably find Hamlet.txt. This is Shakespeare. Hamlet. I'm going to put this in the pilot. Tiny zip. Tiny unzip. Check the output. Looks legit. Yeah, it looks like Hamlet. Rapier and dagger. And let's look at the Finder. So you got 106 kilobytes versus, let's compare with the input. 192. So as you can see, this is a considerable difference in kilobytes. Almost a half of the size is gone. And well, that's how you write a compression from start to finish in Python without using any libraries. Hope you guys enjoyed this video, and I'll catch you in the next one. Peace.